We present a method to design, optimize, and fabricate free-form holographic optical elements, or HOEs. HOEs are thin sheets of polymer, about 10 micrometers thick, on which a volume grating can redirect incoming light in highly controllable ways. This grating is recorded by interfering a reference and a signal wavefront on the HOE, and computing these recording wavefronts is a challenging task. Much like traditional freeform refractive optics, HOEs can be optimized toward a given objective. Here, a pair of HOEs is optimized to design a head-up display system. We present a general method to optimize HOEs for such imaging applications. First, we optimize the X and Y components of the grating to reduce the point spread functions generated by the HOE. Then, the Z component of the HOE is optimized to improve light efficiency. Once the HOE grating has been designed, we show two methods to generate the wavefronts to record the HOE. The first method is to use freeform refractive glass elements to shape the wavefronts, and we propose a new iterative algorithm to compute these glass surfaces. Starting with an HOE and the target grating, we first initialize the two glass surfaces to 0. Then, we trace rays through the glass and collect them on the HOE. If we look at a given point on the HOE, the resulting grating can be computed as the difference between the two wavefront directions, which doesn't match the target grating. We thus project the wavefront directions so that their difference is the target grating that we wish to create. We then trace these new projected rays to the glass, and we compute the new glass surface that will generate these updated wavefronts. By repeating this process multiple times, we converge to a solution where the wavefronts generated by the glass surfaces do approximate the desired grating. Once the glass surfaces are determined, they can be fabricated by diamond turning, and our paper presents multiple results generated with these complex glass elements. A second method to generate the HOE gratings is to use a holographic printer, where the HOE is constructed from tiled holographic patches called hoggles. Designing the ideal wavefront for printing requires to solve a completely different optimization problem. Looking at the frequency content of both wavefronts, holographic printers work best if the bandwidth is contained away from the center of the frequency domain, but remains within the allowable frequencies for the printer. We present a way to move a frequency point into these optimal regions, and by doing this optimization for each point in the frequency domain, we can move all the content in a bandwidth that can be adequately generated by a holographic printer. We show several results using both the printing and the diamond turning approaches, including printed head-up displays, complex lens array profiles, and, for the first time, we create full-color HOEs for caustic and imaging applications. The pipeline we present to design, optimize, and fabricate freeform HOEs unlocks the full potential of HOEs and enables new applications for imaging optics and virtual and augmented reality. Thank you.